There's more terminology. What is a geometric progression? A geometric progression is a sequence with a common ratio between the terms. We should see an example. Maybe the sequence starts 3, then 6, 12, 24, 48, 96, and it keeps on going. And let's say the general rule for this sequence is a sub n equals 3 times 2 to the n. Why is that a geometric progression? Well, there's a common ratio of 2 between each of these terms. To get from 3 to 6, I have to multiply by 2. To get from 6 to 12, I multiply by 2. To get from 12 to 24, I multiply by 2. To get from 24 to 48, I multiply by 2. Right? That's the common ratio between all the terms in this sequence. It's 2. We can write down a general formula for a geometric progression. So I can write a sub n equals the first term, a sub 0, times the common ratio r to the nth power. In this particular example, a sub 0, the first term, is 3, and the common ratio is 2. Well, here's a question. Why are these things even called geometric progressions? Well, in a geometric progression, each term is the geometric mean of its neighbors. Okay, but what is a geometric mean? Well, the geometric mean of two numbers of a and b is defined to be the square root of a times b. Why is a geometric mean called geometric at all? What's geometric about it? Well, here's one geometric story you could tell yourself. You could build a rectangle, one of whose sides is a, and the other side has length b. Then this rectangle has area AB. I'm going to build a square. I'm going to build a square whose area is also AB. What's its side length? Well, the side length will be the square root of AB. So this is some kind of geometric sense in which an average of A and B might deserve to be the square root of AB, a geometric average. So the deal with geometric progressions is that each term is the geometric mean of its neighbors. So let's see that in our original example, 3, 6, 12, 24, and so on. The claim is that in a geometric progression, each term is the geometric mean of its neighbors. Let's see that here. What's the geometric mean of 3 and 12? Well, it's the square root of 3 times 12. That's the square root of 36. That's 6. So yes, 6 is the geometric mean of its neighbors. Let's try it again with 12. What's the geometric mean of 6 and 24? Well, that's the square root of 6 times 24. 6 times 24 is 144, and the square root of 144 is 12. So yeah, 12 is the geometric mean of 6 and 24. The limit of a geometric progression depends very strongly on that common ratio. Well, in our example here, what's the limit as n approaches infinity of a sub n? It's infinity. Because I can make a sub n as big as I like, provided I choose n big enough. What if the common ratio were a third? Well, here's an example of a geometric progression with common ratio a third. 1, a third, a ninth, a 27th, an 81th, and so on. What's the limit of a sub n in this case as n approaches infinity? Well, that's really the limit as n approaches infinity of 1/3 to the nth power, because that's a formula for the nth term in this sequence. Well, that limit is 0, right? By making n big enough, I can make a sub n as close to 0 as I like. Other interesting things can happen too. You should think about what happens when that common ratio is negative.